Okay, so once a hazard is identified, our goal is to get rid of that hazard in one way or another, or resolve it, mitigate it to the lowest reasonable level. Researchers have come up with a hazard reduction order of precedence. This is the preferred order of attack, if you will, for getting rid of a hazard. It gives the organization the most bang for the buck. Essentially, it is starts with the most effective method up here, going to the least effective method down here, and it's in an order of precedence. As you work your way down, you're getting less effective methods of controlling the hazard. Most effective at the top, least effective at the bottom. By the time you work down to the last order in priority sequence, you're really looking at costly methods with a lot less effectiveness of controlling the hazard. And you may notice as the hazard mitigation strategy gets farther down the line, it becomes more and more dependent on the human, which is generally less effective because it's more prone to error, if you will. The most impacting hazard reduction strategy is to design for minimum risk. So we're going to start for the top here and work our way down. Sometimes these top two are combined into one. It's to eliminate or reduce the hazard. Eliminate here, reduce the hazard here. Eliminate, of course, is top priority, but design is the crucial factor here. Designing for minimum risk. This requires prior planning in the concept design phase of the life cycle, because after the system is built and in production, it is much more expensive to go back and redesign safety into the system when after the fact the engineers realize, oops, we missed some hazards that were out there. Sometimes a product has a safety recall. This is an example of where hazards were later identified in the system and designs needed to be improved. That costs the company lots and lots of money. I hope you visited the link in the PowerPoint presentation to the story of the 25 biggest product recalls of all time. Those are examples of where system safety in the design phase went awry. The Toyota airbag safety recall, that tops the list, and it's also implicated in several of the 25 biggest product recalls throughout the list. That one thing cost the company millions. Cost the company millions just to replace the faulty airbag triggers in so many vehicles, but more than 8 lives, 100 injuries were also part of that cost. So not so apparent is the cost of $75 million in fines, lost contracts, lost reputation, lost jobs, lawsuits. Skimping on safety in the beginning generally will cost big time in the end. So next down the line, if the system you are designing has hazards that cannot be designed out or mitigated through design, now you can provide safety devices. Mechanical devices, these are safety devices or mechanical devices that shield the operator from getting to the hazard. The operator, the TTO, the victim, potential victim, is shielded from getting to the HS, that's the hazard source. What you're doing by putting up safety devices, you're blocking the IM component of the hazard, blocking the initiating mechanism of the hazard. It's like a shield on a table saw, for example. We're also relying that the human does not remove the shield and expose themselves to tragedy. If your system does not allow for designing out or designing down the hazard, if your system does not allow for providing safety devices, the next on down the order of priority is providing a warning device. You could provide a warning device to let the operator know when a hazard is present. In a house, a smoke detector is an example that alerts the occupants to the potential presence of a fire. From warning devices on down, now we're going to be relying on the human much more extensively. When an alarm or warning alerts the operator, we require the operator to do something, to do the right thing. Here's an example. The Beechjet, BE-400, a jet aircraft, has a swept wing. It's a very slippery airplane, very fast. Beechjet swept wing design has an overspeed warning alarm. The alarm is obnoxious and it blares when the aircraft goes too fast. The aircraft's design is fully capable of the higher speed, but the danger is with Mach tuck because of the swept wing design. Many flight crews actually pull the overspeed circuit breaker so the alarm will not disturb the passengers in the back. They may not understand the reason for that safety device. That's an example of humans overriding safety and warning devices, as removing the guard on a table saw. If none of the above works, then special procedures must be employed to mitigate the hazard. This is by far the least effective hazard reduction strategy, but it's also the most widely implemented. Okay, it's the least effective because it requires the human to do the right thing at the right time, all the time, to remember to do the right thing. Special procedures that's like checklists, maintenance procedures, operational procedures, etc. As by the time we get to this point, if the engineer has intentionally worked down through the hazard mitigation precedents, it should give the engineer ample opportunity to think outside the box and try to work out ways to mitigate the hazard. However, keep in mind that if it cannot get to an acceptable level, the risk may not be worth the reward. Mitigating the hazard is one thing, but we can only mitigate what we know is there. Identifying the hazard sometimes is the most difficult part of system safety, as we have said before. In the next video, we'll go back to discussing hazard analysis types, systematic ways that we can work through the system to identify hazards throughout the system. So then, what we know is there, we can work through this hazard reduction precedence to mitigate the hazard, to eliminate the hazard, or to mitigate it down to an acceptable level.